the rate of change of y, that's our dy dx. When we see is in a problem, what's that tell us to put? Equals. And then proportional to, when something is proportional to, that means that there's going to be a constant of proportionality, so like a number that we can multiply this value by. So proportional to, the letter you see used most often for this is a K, although it technically could be any letter, except for probably Y or X, is proportional to the value of Y. So value of Y is just Y. So this is the differential equation that you end up with when you read this off. The rate of change of Y is proportional to the value of Y. So it's dy over dx equals some number times whatever letter it says it's proportional to. And that, let's write down that K, K is the constant of proportionality. So, if I want to solve this differential equation, then I need to multiply both sides by dx. And then I also need to get rid of this y over here, so I'm going to divide off that y. So I end up with dy over y equals k dx. And keep in mind, k is a constant. It is not really a variable like x or y. Question so far? All right, then we will integrate both sides. And when we integrate both sides, we're going to have natural log of the absolute value of y equals kx plus c. And typically, we want to have this solved for y most of the time whenever we have that natural log. So we're going to make both of these powers of e. We just get y on that left-hand side. And here, what's going to happen with this c over here? It's going to be c, and is it going to be added to the end or multiplied over here? Probably best for you going home, Joe. Probably best for you going home. Yeah, you need to. Yeah, going home. Yeah, you've got to. If you wanna not. Okay, so this c right here, will it be added or multiplied? Multiplied. So we'll have c e to the k times x. Now, this should seem kind of familiar to you because this is something that you have used before, but just some of the letters are different. Do you guys remember? Yes, this is PERT. P-E to the R-T, right? This is the same form. Here, P-E to the R-T, P is principal because usually it's used for like investment sort of stuff. Not usually taxes, but like investments. So P is principal, E to the r is your rate and t is your time. So here, this is just sort of a more general form, ce to the kx, where it is really the same thing, but it's a little more general and not specific to interests, but could be used for interests here. So, if you read this, the rate of change of y is proportional to the value of y, then that means you're going to end up with y equals ce to the kx or kt or whatever you want to use. Call it y equals pe to the rt. That's fine if you want. So we are going to do a lot of problems of application here. When we do them, we can skip all the calculus really. When you read this, and on the exam, now if it's on free response, which typically these are not. Typically these are usually on the multiple choice section. If it's on free response, you should try to set up this and integrate. But if it's on multiple choice, when you read this, you want to have red flags going off in your head that tell you, oh, this is PE to the RT. And then know to use that to solve the problem. You don't necessarily have to do the integration there. So the first problem we're going to look at, these pages right here are not right. This is, you can just put a note in your notes there. These are from 378 to 380. And they're like if it's example 2, it's example 2 there. So this is one type of problem that you might see. It says the rate of change of y is proportional to y. Whenever you read that, the rate of change of y is proportional to y, you should be thinking y equals, usually I use ce to the k, well I guess in this case, it doesn't really matter, kt, you can use whatever, yeah they use a t here, so t and y are the variables that they use. So it says when t equals 0, y equals 2. When t equals 2, y equals 4. What is the value of y when t equals 3? Okay, so we don't even really have to do the calculus part of this, as long as we recognize this is what is meant here. So we're going to use the information they gave us. We really need to find c and k, because both of those are constants for this equation. So the one we want to use first is whichever one has t equals 0. Because if we plug that in, when t equals 0, y equals 2, so we would plug in 2 for our y. We've got ce to the k times 0. We want to use that one that has the 0 first, because k times 0 is 0, so the k will go away, and we will be able to solve. So 2 equals ce to the 0. What is e to the 0? It's 1. So this c is just 2. So now we've got y equals 2e to the kt. Now we can use the second set of information that they've given us. When t equals 2, y equals 4. So we'll have 4 equals 2e to the k times 2. Now this one's going to be a little bit harder to solve, but not too bad. You're going to divide off that 2. So you got 2 equals e to the 2k. What would you do next? Natural log, because we're trying to solve for the k, right? So we've got to get rid of that e. So we take natural log of both sides. It'll cancel over here. So we got natural log of 2 equals 2k. And then we just got to divide by 2. So k is natural log of 2 over 2. So now we've got our full equation. Y equals 2e to the natural log of 2 over 2 times t, or you might want to get a decimal there. Either is fine. And then the last thing it says, what is the value of y when t equals 3? So now we can just plug in 3. So we get y equals 2e to the natural log of 2 over 2 times 3. And at this point, we'll definitely grab our calculator and type that in. Button, blue, and x. Okay, yeah. Natural log of 2 over 2 times 3. Okay, and so we can get 4 root 2, or if we want a decimal, hit the green button, and we get 5.65. Yeah, I'm recording and the homework will be on Canvas, so I hope you feel better, Doug. I think so, yeah. I know in elementary school, yes, definitely. So. Feel better. Okay. Alright, so let's look at one where there's some like real application, because exponential growth and decay has a lot of application in real life. This is also from the book. It's example 3 there, and in the book there's a picture there. Does it say when it happened? I didn't copy the whole thing. I remember it, the tsunami that happened in Japan and caused the Fukushima nuclear disaster, where plutonium was leaked. This, is a major problem. Nuclear power is very efficient and very, kind of like clean for the environment, as long as you don't have any problems. Yeah, as long as you don't have radioactive material leaking into the environment. But if you do, the effects of that are so bad that's why everybody is, hesitant on any type of nuclear power, or a little bit scared of it. I don't really want them to come put a nuclear power plant in my backyard anywhere. To look at an example, it doesn't say. Does it say how much the actually leaked out there? I should have copied the whole thing. Or how much was? I don't think it does. They probably don't want us to know. The government will never let us know. So if we had 10 grams of plutonium were released in a nuclear accident, how long would it take for the 10 grams to decay to 1 gram? Okay, and it doesn't tell you this. Right in the problem, but there's a chart above, and that plutonium has a half-life of 24,100 years. Much longer than I plan on being around. So, by about 24,000 years or more. So, what we want is to figure out an equation equation that we could use so we can figure out how long it's going to take for just 1 gram to be left. Because we could kind of get an estimate. Like, I know it's going to take 24,100 years for there to be 5 grams. Right? And then it would take another 24,100 years for there to be 2.5 grams. So I can keep dividing, but I won't get exactly to 1 if I do that. So I need to know an equation if I'm looking for this. So, so what we're going to do here in a half-life situation, this is exponential decay. We can start with y equals ce to the kt. And right here, I know that C is going to be 10 grams. If I wanted to, I could go through this whole thing, like where I plug in y equals ce to the k, time is 0, and I guess we put y is 10 here. But that's always going to end up where just your C is 10. So we know C is, whenever we did PERT formula, that was our principal value, the amount that you started with. So it's the amount of the plutonium that you start with here. So we're going to have y equals 10e to the kt. But unlike the other problems, this did not give us like a second time, like we know at, we know at 5 years that there's this much left. So what could we do? Because we really need the k to get us an equation, right? So what could we do to find that k? Very good. There's 5 grams after 24,100 years, right? So we could plug in 5 for our y, because that's half of what we started with. And for our t, we could plug in 24,100 years. All right, and now we can solve for that k. So we would divide by 10. So we'd get 1/2 equals e to the 24,100 k. If we got to get rid of that e, what do we do to get rid of e? Natural log of both sides. And then lastly, we'll divide by 24,100. I imagine this is going to give us kind of a crazy answer here. So we do natural log of 0.5 divided by 24,100. We're going to get negative 0.000029. We want to store this number in our calculator because especially with exponential growth and decay, if I round that off, even if I just round it off to like 0.00003, by the time I am looking, hundreds of thousands of years down the road, that rounding is going to throw my answer way off because the little bit you rounded is going to grow exponentially, just like the problem. So let's store this as, I guess K would be a good thing to store it as. But I can't read. No, that's H. K's here. Okay, so we'll store that as K. And you can see it stores a lot more decimals there if you actually store it than just what you see there. So, so our equation is y equals 10e to the negative 0.000029t. The button right above the on button is the store button, so you just hit that button and then whatever letter you want to store it as. And so now I've got my equation that can give me the amount of radioactive material left at any time. What did the question ask us for? For when there's 1 gram. What do I plug the 1 in for? The y. Alright, so we're going to plug in 1 for our y. divide by 10. We get 0.1 equals e to negative 0.000029 t. What's next? Natural log. So I've got natural log of 0.1 equals negative 0.000029 t. What should I do now? Divide. And whenever I do that, I'll do natural log of 0.1 divided by k. We'll sort that value. And t is 80,058.5 years. Definitely showing why radioactive accidents are a really, really big problem, because it's not something that goes away quickly. Yes. Really? Mm-hmm. He got a little carried away. I took my pre-cal class. Got a little carried away. Even though he did not talk to us very much about anything they actually do, so I would have really rather heard about like those sort of things. Most of what he talked to us about was like scholarship opportunities and stuff. But that's what I think that's what Emily Lane's brother does. He works down in Charleston, and he's like in the nuclear program. He was super smart. So, but yeah, I don't think I'm signing up. Yeah, you're right. I might have to. I will say this: if I get drafted, I'm gonna try to go into the nuclear engineering program instead of the front lines. Yeah. Yeah. I feel like maybe I've got some math skills they could put to use somewhere instead of sending me to the front lines, because that would not go well. But, or Canada's not that bad of a place. Buy some warm clothes. Take my children. So, hopefully we won't reinstate the draft anytime soon, especially since they can. Yeah. Alright, so radioactive decay is definitely one area this can apply. Another thing that you look at really often is exponential growth of populations. So example 4 has an experimental population of fruit flies. And I can speak from personal experience that if you ever get those stupid things in your kitchen, they multiply exponentially, and it is hard to get them to go away unless you just like bleach down your entire kitchen. Like I usually just leave like apples or something sitting out in a little bowl. But if you have apples sitting out in a bowl and you've got fruit flies, oh, it's bad. So there are 100 flies after the second day of the experiment and 300 flies after the fourth day. And it wants to know approximately how many flies were in the original population. So in this case, this problem is a little different because this problem does not give you the time 0, right? It's asking us for the time 0. Let me look back through something real quick. Hold on. I've got to check my notes right here and make sure I can do what I want to do. Here. It's a while. Let's pause this. Alright. So, population increases according to the law of exponential growth. There were 100 flies after the second day of the experiment, and 300 flies after the fourth day. Approximately how many flies were in the original population. So, we know T equals 2 is a Y of 100, and we know T equals 4 is a Y of 300. The book gives a different way to do this, and you can look at it if you want, but I think it's a little confusing. So this is what I would, and the question is asking us for T equals 0, right? So I think that this is much easier. So if they give you something like this where your original time is not 0, right? The first thing they give you is like T equals 2 in this case. This is what I would consider doing. I'm just going to make this 0. Call the second day the actual beginning time. So if I do that, what does that turn my 4 into? A 2. What does that turn my 0 into? A negative 2, right? It's going to answer the same question. My equation is going to be different. This method might not work if they asked you for an equation, although we could still get the equation this way. But, so what I can do now is I can just say Y equals, the initial population now is 100, E to the KT. So I could plug in the 2 and the 300. So 300 equals 100 E to the 2K. Divide by 100. I get 3 equals E to the 2K. Take the natural log of both sides. So the natural log of 3 is 2K, and then divide by 2. So I get that my K is natural log of 3 over 2. And if we do that in the calculator, we're going to get K is 0.549306. The book does it a different way, but they get that exact same value as K. So I feel confident that this is just as good and easier to understand. So we've got our K. So now our equation is Y equals 100 E to the 0.549T, and we're going to store that value in our calculator or use natural log of 3 over 2. So if we want to know how many flies were in the original population, what have we got to do now? Not T is 0, negative 2. Because the 0 we changed, it really isn't our 0, it's really our second day, but we just called it our 0. So we'll plug in negative 2. So we'll have Y equals 100 E to the 0.549 times negative 2. And here, when you do this, 100 E to the, I'm going to do natural log of 3 over 2 times negative 2, so I don't round anything. And bring that in the inner. And so we'll get Y equals 33.3 repeating, but you can't really have a third of a fruit fly, so you would just say 33 flies. Mm-hmm. The problem is if we use the 2 and the 4, then that means that we've got Y equals CE to the KT, little k, KT, and C is your initial value, right? So, like, if I know T is 0, I can just plug in 100 for that C. If it's not, then I've got to plug in 100 here and CE to the 2K, and I can't really solve that for anything. I could also make another equation where I've got 300 equals CE to the 4K, and then I could solve them both for K and set them equal to each other and find the K, but yeah, it takes a long time. This way is a lot quicker. So by renumbering our days and using sort of backwards days, we can find this a little bit quicker. All right, questions? All right, go ahead.